Welcome to today's session about the hydraulic design and optimization of multistage pumps. So what are the reasons for using multistage pumps? The achievable specific work Y for a single pump stage is limited. This can be due to mechanical strength limits, like the circumferential velocity U of the impeller, or due to flow-related limits, like the wear coefficient psi, where the performance drops off quickly outside of the recommended range. If the maximum specific work of a single pump stage is reached, it is recommended to use multiple pump stages. What other benefits can one get from multi-stage pumps? Well, we can easily increase the head and operation range by just adding additional stages to the machine. We achieve an overall better packaging due to smaller impeller diameter. A smaller plate tip clearance is achievable, and we are able to design more efficient impellers. In this graph on the right-hand side, you can see the achievable hydraulic efficiency over the specific speed of the pump for different volume flow rates. Let's assume we want to design a pump for a specific duty point. A single stage pump would result in a very low specific speed and therefore in a low overall hydraulic efficiency. But if the specific work is distributed among multiple pump stages, we are able to create a pump design with a better overall efficiency. So for this session we have created a multi-stage pump design in our conceptual turbomachinery design software CFTurbo. The duty point is defined by a volume flow rate of 10 cubic meters per hour, approximately 44 gallons per minute. We wanted to achieve an overall head of 20 meters, so 66 feet, at a rotational speed of 3,600 revolutions per minute, and we used water at 20 degrees as our transportation fluid. In the lower right corner, you can see the resulting design in our design software CFTurbo, consisting of the 3 pump stages. One pump stage consists of a centrifugal impeller and a bowl diffuser, and we also modeled some adjacent turbomachinery components upstream and downstream. For the duty point evaluation of our turbomachinery design, we chose to use 2 solvers. On the one hand, we used ANSYS CFX with a segment model and performed steady-state simulations on a mesh with 1.3 million nodes. On the other hand, we used the Simerix MP solver with a 360-degree model. We performed steady-state and transient CFD simulations with a computational grid of 4 million nodes. If we take a look at the tabular CFD results of our duty point evaluation, we can see that both solvers confirm CFTurbo's initial design for the duty point of 20 meter head. The simulation results from ANSYS CFX and CFTurbo SMP are pretty close together, as you can see right here. We can see that the difference between a steady state and a transient simulations are only minor. Additionally, we can see a certain drop in head and efficiency when comparing the first stage with the second and third one. So let's see. For the first stage, we achieve an overall head of 7.8 meters, but when comparing it with the second and third stage, you can see that there's a certain drop. The same results can be seen from the efficiency. So for the first pump stage, we achieve an overall efficiency of 92.6%, whereas the second and third pump stage only achieve an overall efficiency of 91.4 or 91.3. So we conclude that the impeller efficiency is quite excellent, but if we compare the impeller efficiency to the overall efficiency of the machine, we can see that there are some losses occurring in adjacent components, and therefore we should conclude that the diffuser design should be improved. If we take a closer look to the CFD results, we can see that there are some local flow separations occurring in the bowl diffuser. So in this image you can see streamlines in a plate-to-plate view for the midspan. The flow comes in from the left-hand side, and we can see that the flow is nicely attached to the impeller plates in the moving frame of reference, whereas we can see local flow separations inside of the plate passage of the bowl diffuser. If we visualize the CFD results in the 3D model, we can see some vortex formation inside of the plate passage of the bowl diffuser for the CFD results of ANSYS CFX, similar to the plate-to-plate view from the previous slide. This is also confirmed by the results from the Simerix MP solvers, where we can see this flow pattern occurring in all three stages. So we conclude that this is more of a general flow problem. So in the next step, we wanted to optimize the bowl diffuser design to further improve the overall efficiency of the machine. For the geometry modeling, we used our Conceptual Turbomachinery design software CFTurbo. For the meshing, we have used TurboGrid, and for solving the CFD problem, we have used ANSYS CFX. The sensitivity analysis and the optimization was performed by using Dynarus OptiSlang. On the right-hand side, you can see the workflow that was set up inside of ANSYS Workbench. CFTurbo creates the turbomachinery design, controlled by parameters inside of the parameter set, and then we transfer the geometry to TurboGrid to create the computational meshes. Inside of the CFX system, we set up our flow problem and solve it, and then we transfer results back into the parameter set. Additionally, we attached a sensitivity analysis and an optimization system to this workflow. In order to keep the computational costs low, we only used a reduced model where we only model a single pump stage, including with some artificial outlet and inlet extensions. We started the bowl diffuser optimization by creating an initial design of experiments, short DOE, with 23 geometry parameters. 14 of these 23 geometry parameters were used for the meridional design of the bowl diffuser. These were mainly contour control points as well as points for the meridional edge position. On this right-hand side, you can see how these control points were able to move in the meridional space. So for example, for the leading edge, we have control over the leading edge position at the shroud as well as the hub, and we are able to move these control points in upstream or downstream direction. The same can be done for the trailing edge. You can see we have independently controlled points for the trailing edge position at the shroud as well at the hub, and of course the hub and shroud contour are designed by using Bezier curves, and we are able to move the control points of these Bezier curves in radial and axial direction. Additionally, we were able to modify 5 parameters for the bowl diffuser plate properties. So these were mainly plate angles for the leading edge and trailing edge at different spans, so hub and shroud, and we also were able to modify the number of plates of the bowl diffuser. And we had 4 parameters for the mean line design, so these were mainly the rake and the wrap angle at different spans. From the CFD analysis, we got at all 7 responses. So these were the efficiencies for the impeller as well as for the pump stage. We evaluated the shaft power. We evaluated total and static pressure at the bowl diffuser outlet right here. And of course, we evaluated the total pressure difference of the impeller as well as the total pressure drop inside of the bowl diffuser. For our initial DOE, we have used a Latin hypercube sampling, and in this graph you can see the total pressure drop inside of the bowl diffuser for the y-axis and the static pressure at the bowl diffuser outlet on the x-axis. The green dot marks our baseline design, and scattered around this baseline design you can see the different designs created by the Latin hypercube sampling. You can imagine that by reducing the total pressure in the bowl diffuser and by increasing the static pressure at the bowl diffuser outlet, we want to move our optimized design in this target area. And we need to formulate objectives for our own optimization. And in this case, we want to maximize the static pressure at the bowl diffuser outlet. And this can be done by reducing the internal pressure losses inside of the bowl diffuser and reducing the swirl component at the bowl diffuser outlet. We used suitable designs from our Latin hypercube sampling as an initial population for an evolutionary algorithm, and on this right-hand graph you can see that we were able to further improve the design by reducing the internal pressure losses. And you can see that the optimization algorithm performs well since most of the designs are moving closer to our target area. So if we take a look at the overall CFD results from our bowl diffuser optimization, you can see that for the total pressure drop inside of the bowl diffuser, we were able to substantially improve the design just by running a simple DOE, and we were able to further optimize the design by running an optimization. So all in all, we were able to reduce the total pressure drop in the bowl diffuser by 42%. If we take a look at the static pressure at the bowl diffuser outlet, you can see that compared to the baseline design, we were able to increase the static pressure by 4%. If we take a look at the total pressure difference, you can see that the total pressure difference inside of the impeller remains unchanged. This is plausible since we did not modify the impeller design. But if we take a look at the total pressure difference of the stage, you can see by running the optimization, we are able to improve the total pressure difference by 4%. And lastly, if we take a look at efficiencies, it's similar to the total pressure difference. Since we did not modify the impeller, the efficiencies in the impeller domain remain unchanged. But if we take a closer look at the stage, we were able to improve the stage efficiency compared to the baseline design by 4 percentage points. So let's visualize the results from our bowl diffuser optimization. So if you remember, for the baseline design, we have seen some vortex formation inside of the plate passage of the bowl diffuser. And if we take a look at the optimized design, you can see that this vortex formation is gone. The flow stays nicely attached to the plates inside of the bowl diffuser plate passage, and also the flow outside of the bowl diffuser more upstream looks a lot cleaner compared to the baseline design. So the previous data were results from our bowl diffuser optimization using steady-state CFD analysis on a reduced computational model which only reflects a single pump stage. In the next step, we perform transient CFD analysis on a multistage 360-degree model. When it comes to the head of our multistage pump, we were able to increase it by 2% by running an optimization. When talking about the efficiency of our multistage pump, we were able to increase it by 2.5 percentage points. And if we take a closer look how it is distributed between the stages, you can see that comparatively stage 2 and stage 3 show larger gains compared to stage 1. If we take a look at the shaft power, you can see that we were able to reduce the overall shaft power by 1 percentage point, and you can see that especially stage 2 and stage 3 shown gains comparatively larger compared to stage 1, which is the result of an improved design that also provides a more uniform flow field with a smaller circumferential velocity component. So after successfully optimizing our bowl diffuser design, we wanted to further improve our impeller design, especially when it comes to the required NPSH. So for the geometry modeling, again, we have used our conceptual turbomachinery design software CF Turbo. For the meshing and CFD solver, we have used CF Turbo SMP, which makes use of the Semerics MP solver. And for the sensitivity analysis and optimization, we have used the open source optimization framework Dakota. On the right-hand side, you can see the workflow setup that was used to optimize the impeller design. We have used tools provided by Dakota, the capabilities of CF Turbo, and tools provided by Semerics MP. Again, we have used the reduced model. We have replaced the bowl diffuser design with an artificial outlet extension, since we are only focusing on the inlet geometry of the impeller, but we have used a real geometry to accurately model the inflow conditions for the impeller. So for the optimization of the NPSH, we were in the need to run multiple steady-state analysis with an activated cavitation model for each design iteration. In order to keep the computational costs low, we have used a reduced model. And what were the steps we have used for each design iteration? Well, we started with a steady-state analysis under cavitation-free operation conditions, and for these analysis, we evaluated the flow quantities of interest. Then we performed another steady-state analysis, but this time under the presence of light cavitation due to a lower total pressure at the model inlet. Then we calculated the relative performance reduction between these two CFD analyses for each design iteration. So similar to our bowl diffuser optimization, we started the NPSH optimization of the impeller with an initial design of experiments, short DOE, where we modified 6 geometry parameters. 3 of these 6 geometry parameters were used for the main dimensions and the meridional design of the impeller. So for example, we modified the suction diameter of the impeller as well as the meridional plate position for the leading edge, a shroud, as well as hub. Additionally, we had 3 parameters for the impeller plate properties, which was the plate incidence at hub and shroud and the plate thickness at the leading edge. From the CFD analysis, we got 2 responses. On the one hand, we got the efficiency of the impeller under cavitation-free conditions, and we got the relative total pressure drop due to cavitation. So similar to our bowl diffuser optimization, we started the optimization of our impeller by running an initial design of experiments using a Latin hypercube scheme. Displayed in this graph, you can see the results from the sampling, and on the y-axis, we have the relative total pressure drop inside of the impeller domain due to cavitation effects, and on the x-axis, we can see the impeller efficiency under cavitation-free conditions. Our black dot marks our reference design, and scattered around you can see the results from the sampling. You can imagine that we want to move in this target area by reducing our total pressure drop due to cavitation effects and increasing our impeller efficiency. After the sampling, we ran some statistical post-processing on these samples. We have plotted a correlation matrix with antle plots, and from this we can get correlation coefficients for parameters in respect to responses, but also input-input correlations and output-output correlations. So after running an initial sampling, we selected the most promising designs and formed an initial population for a multi-objective genetic algorithm, and displayed in this graph you can see the results from this optimization. So you can see just by running the optimization we were able to further improve the impeller efficiency as well as the impeller performance under cavitating conditions. If we zoom in a little bit further, you can see we started right here with the black dot, which is our reference design. Then we were able to improve this design just by running a sampling, and again we were able to further improve it by running an optimization, and in the end we got a Pareto front, and from this Pareto front we selected Pareto optimal points displayed as red dots. So let's take a look at the final data of the optimization. So as the multi-objective genetic algorithm progressed, it tried to maximize the impeller efficiency and minimize the cavitation-induced performance drop. And as we can see from this data, the design sort of hit a barrier where the optimization algorithm is not able to further improve the design. And we said, okay, this is probably going to be our Pareto front. And from this Pareto front, we selected 4 Pareto optimal points to further conduct additional analysis on these designs. So for each design behind these Pareto optimal points, we calculated the drop curves by using multiple transient simulations, and from this we got the required NPSH. And if we take a closer look at this right graph, you can see we have the NPSH required on the y-axis, we have the impeller efficiency under cavitation-free conditions on the x-axis. We started with our reference design right here, and just by running the optimization, calculating the drop curves using transient simulations, we were able to improve our impeller efficiency by 2.1 percentage points, and we were able to reduce our required NPSH by 23%. And what's quite interesting is that the steady state trends from the optimization right here provide a good estimation for the required NPSH trends we can see on the right hand side that we got from transient simulations. So let's come to the conclusions of this talk. So in this session, we presented results from automated turbomachinery optimizations. We shown the hydraulic design optimization of a bowl diffuser using a parametric conceptual design software, which was fully integrated into an industry-leading simulation framework. Additionally, we provided a guideline to systematically improve the hydraulic efficiency and the required NPSH value for a multistage pump. And what was interesting, that the reliability of the tendencies seen in the steady state results of the optimization were verified by fully transient simulations. So if you have questions about this talk, feel free to contact me or my colleague, and we are happy to answer your questions. Thank you very much.